So we've learned how to write equilibrium expressions for different equilibrium reactions, and we've been looking at the concentrations. Well, what if we have gases? Could we use, say, their partial pressure instead? And yes, we can. So in a gaseous reaction, the partial pressure of a gas is proportional to its concentration. And one way we can look at that is, PV equals nRT. What are the units of molarity? Moles over liters, right? So if I divide this side by volume, this is molarity. So the partial pressure of a gas is equal to its molarity times RT. Kind of cool. So when we write these expressions using pressures, we use the same pattern, except instead of calling it Kc, we call it Kp, and we're looking at partial pressures for each of the gases. The business with the exponents is all the same. These pressures are in atmospheres. The value of Kc is sometimes the same as the value of Kp, but not always. So that's kind of confusing. But there is a relationship. Because the partial pressure in atmosphere is not the same as the concentration of molarity, and like we just looked at, the partial pressure of a gas is going to equal its molarity, N over V, times the ideal gas constant times the temperature. Or we could say that molarity, N over V, is equal to P divided by RT. Everybody okay with that? So if we take, instead of the concentration of A, we take the partial pressure of A over RT, which we just showed is the same, and stick that into our generic equation, then what do we have? Well, let's look at this. Kc is in terms of concentrations, right? So this would be, nope, not A. C to the C and D to the D over A to the A and B to the B. So if we plug in the these partial pressures expressions here, so we've got the pressure of A over RT raised to the A power, not A, C. And the pressure of D over RT raised to the D power divided by the pressure of A over RT raised to the, that's supposed to be a C, because A is down here. Pressure of B over RT. So I took the ideal gas law, PV equals nRT, old friend from Chem 1A, and I rearranged it. Moles over volume in liters is the same as molarity, and that's equal to the partial pressure of a gas divided by RT. And so I plugged those things into here. Let's try to simplify this business. Well, let's try to pull all of those RTs out. So we're going to have PC to the C power. What's the best way to write it? Times RT to the negative C. So because this is in the denominator, instead of making more fractions, I'm just going to put a negative in front of the exponent, because 1 over x squared is equal to x to the minus 2, in case you don't remember. And then we have PD to the D, and we have RT to the negative D. Can't blow stuff off when we're wearing a stupid mask. A to the A, RT to the negative A, B to the B, RT to the negative B. So that doesn't exactly look simpler, does it? This and this and this and this is what is the expression for PC. I mean KP. Gosh. So let's pull that together and see what we can do with the rest of it. So these all have negative exponents. I can get rid of those by putting them on the opposite side of the fraction. So I put this one in the denominator and that one in the numerator. So now I've got RT to the A and RT to the B divided by RT to the, oh, I know what I wanted to do. I'm going to bring those up, and I'm going to leave the other guys up there. RT to the negative C and RT to the negative D. Now, when you're multiplying things that are raised to a power, what can you do to simplify this? We can factor the RT out, and then what can we do with the exponents? Add them. So this is going to be RT to the A plus B minus C minus D power. Well, what is that? That is the difference in moles between the reactants and products. So I take the total number of moles of gas in my reactants, I subtract the total number of moles of gas in my products, and that's going to be the exponent there. And so we say that Kc is equal to Kp times RT to the delta N, change in moles. Keep my fingers crossed that that's what it says on the next slide. Yes. No. What's wrong? I got the P's and the C's mixed up. How did I do that? Oh. I know. Because this is something I have a hard time remembering. The way I have this set up, we're taking the reactant moles and subtracting the product moles. Is that how we usually do things? No, we're always taking the final and subtracting the initial. So what delta N is equal to is C plus D minus A minus B. And so the way it's written over here, this is actually negative delta N. And that's just a big old mess of a derivation. But that's the equation. Okay, questions? If you have the same number of moles of gases on both sides, those RT factors will all cancel each other out, and Kp is equal to Kc. But that doesn't really happen all that often. And so we need to know what to do when they are different. So here, delta N equals moles of product gases minus reactant gases. And we're only interested in the gases. So consider the following reaction and corresponding value of Kc. What is the value of Kp at this temperature? So we need our little equation. So Kp is equal to Kc times the quantity RT raised to the delta N. So what is delta N in this reaction? How many moles of gas products do I have? Two. And how many moles of gas reactants do I have? Two. When delta N is equal to 0, this term goes to 1. Kp equals Kc, which equals 6.2 times 10 to the 2. That one was like, a little too easy, but whatever. Okay. So what about units on K? Because we're taking molarities and multiplying them and dividing by molarities. But they're going to be different for different types of reactions, right? Some of them, all the molarities would cancel out, but others, you could end up with moles to the negative third or something. So what we're actually doing is we're talking about an activity, the activity of the species, which is the ratio of the concentration or the pressure to a reference point, which is 1 molar or 1 atmosphere. So if you have a concentration that is 0.5 molar, and you do the activity, that's 0.5 molar divided by 1 molar, which equals 0.5. No units. Same thing happens with the pressures. You measure the pressure in atmospheres, and it's divided by atmospheres, so the atmospheres go away. I overlooked that I actually have a little example there. This was supposed to be a 3, I guess. So as long as we're using molarities for Kc and atmospheres for Kp, we can just drop the units on K. And we're not cheating or anything. They made up this excuse that we can do that. Okay, under which circumstances are Kp and Kc equal for the reaction shown here? We've got three choices. If A plus B equals C plus D, if the reaction is reversible, if the equilibrium constant is small. Kp equals Kc times the quantity, or T, delta N. Delta N is equal to C plus D minus A plus B. So it's going to be A. Any questions?